Welcome back, campers, to another episode of Dan's Pro Shop. Today, we're talking about relays. And please excuse the mess, there's just so much crap going on right now. Anyway, I released a short a while back about relays and briefly how they work and what they do. But I put this together as kind of like a testing thing to just do different bench tests and stuff and simulate like a control station or an operator station on a machine. But it ended up being a really useful thing, and I feel like this is a good learning tool. So you guys left a lot of good comments and questions on that short video, and I feel like we could embellish a little bit more on that, something more than what 60 seconds would allow in a short. So if you guys are interested, let's check this thing out, see how I put it together, and you guys can better understand how a relay and a control station works. Let's check it out. Now we're over here at the operating table. Let me better explain to you what's going on. What we have here is a regular 8-pin ice cube relay. I simply just took the plastic covering off of it so you guys can better see the guts and how this thing operates. So if you guys are familiar with these are super industry standard, nothing crazy. This one just happens to be 115 volt coil, and it's good up to 250 volts, I think 10 amps. So I have that plugged into just a regular relay socket, Automation Direct. These things are pennies on the dollar. Automation Direct, you're awesome. Thanks. And to simulate some outputs here, I simply just have a red and green LED on the output. You'll see here in a moment, I have the red one on the normally closed side of the contact, and this one is the switched leg of that contact. We have our power here on the common side of that contact that's switched, our neutrals bonded together, and then down here is our coil. Let's see if we can't get this thing apart. Okay. Now you guys can see here the 8 pins of this 8-pin relay and how they index. And check this out here, how there's this little notch in the receptacle here. That's so this index is only one way. So you can't screw this up when you put it in. Whenever you wire something to pin number 4, it's gonna be pin number 4 on the relay. That's just one of those things that's just nice to have, so you can't screw it up. So just a brief overview of the function of a relay. I know these things are old and antique, and we've really gotten a lot further in today's technology with solid state relays and MOSFETs and everything. But let me tell you, brother, these things are still extremely prominent in industry. You will run across these all the time. Yes, they may be old, but they are reliable. These things are still around all of the time. The way this thing works is there's an electromagnetic coil here that operates on whatever control voltage your machine is supplying. In this case, it's 115 volts, 120 volts. You get the point here. But there's also higher ones, 220, 240, 480, whatever you need. Just in this case, it happens to be 115. So on this particular one, and 90% of them like it, pin number 7 and pin number 2 are for your coil. So you would put a hot and a neutral of 115 volts across these 2 pins to energize this coil. When this coil is energized, it creates a magnetic field that sucks this switch down from its normal position. Now you see how this thing moves but goes back? That is because of this spring right here. That holds this lever in one particular position, and whenever this magnet is turned on, it defeats this spring tension and turns this switch into the normally open position. So here we have normally closed, and that's normally open. And we can control the position of this with this coil. That's easy enough to do with a push button station or a limit switch or something that would trigger this to come on. And the beauty of this whole little thing is that we can control some outside source or some function or something to happen simply by a button press or by something else happening. And another really cool thing about relays is that we can control a much higher voltage or a higher amperage load with a smaller voltage or a smaller current. And that is one of the biggest beauties about relays, is that I can control something bigger with something significantly smaller. And that's really the basis of a control circuit. That way, whenever we go to the operator station, I can use 115 volts or 24 volts or whatever, something that's relatively safe for a human operator, and I can control potentially 400 or 600 or 1,000 volts on the switched leg of the relay and not be exposed to that at my button. So I can use 115 volts to operate this, and I can potentially control way higher power on this side. Now that we kind of have a grip on how the relay works, I'm going to take this thing apart and show you how I have this together. It's super simple, but this is a really good explanation of how an e-stop circuit would work in a control system. So you guys can tell here, this is about as crude as it gets. I have a single gang like switch box here that I simply just put some buttons into a blank plate. I got some KOs here with cord grips, a regular cord going in one side just so I have supply and control power, and coming out of the other end I have a neutral, a normally closed leg, and a normally open leg. So the normally closed is operated by my e-stop here. So whenever the e-stop is pulled out, this is energized to simulate control power. If I push the e-stop in, it kills absolutely everything to simulate an e-stop in a machine. So it would kill the control circuit totally. Whenever this is out, this normally closed leg is on, and I have the ability to operate this normally open circuit. So I can use the normally closed to operate my control circuit, and I can use my normally open to operate a function on that control circuit. And we simply have the neutral to go back so we can have everything function correctly. Now let's tear this thing apart so I can show you guys a little bit of the wiring. Now this is another kind of industry standard thing that you will run across in push buttons. A normally closed is red and a normally open is green. This isn't the case all of the time, but more often than not, this is what you're going to run into. So even if you don't have the notations here that tell you what they are, you should be able to know just by the color. And if you don't have either of these in that weird scenario, you can always tone these things out with a meter and then just play with the button and see which position this thing is in normally. So you guys can tell here, coming in from the left, this is my supply power. I have my hot leg of 120 volts, and then I have my neutral. I have a connector here, just in the case that my field wiring gets damaged or I need to change something. It's easy enough that I can disconnect this side from the box and then suit it for whatever situation I might need. But I have my hot leg coming in directly to the e-stop. This is super important, and this is what you would normally see in a control circuit in a machine. Everything goes through the e-stop first, because in the event this e-stop is depressed, it kills everything downstream. So, I mean, it's in the name, emergency stop. If you hit this button, you want everything to stop. So I have the main power coming into the e-stop, and then I have my normally closed leg over here coming out of the e-stop to my field wiring. I also have a jumper coming out of the e-stop and into the input side of my normally open switch. That means that this switch is only energized whenever the e-stop is pulled out. So if the e-stop is depressed, this switch is open and this little jumper wire has no voltage, and this switch will do nothing. You can press it till the cows come home and you got nothing until the e-stop is out. And this is a perfect prime example of something we call series wiring. Now, if you guys are familiar, there are two very specific kinds of wiring. There are parallel and series. This particular one is series, meaning that my power comes in this side of the e-stop, goes through the switch, out the other side, through a jumper, and into the start of this switch. So in order for this wire here to be energized, it has to go through two switches that have to be in a certain position. Now, if this were to be wired in parallel, meaning that my incoming voltage power here would go to this side of this contact and also this side of this contact, meaning that both of these switches would work on their own regardless of the position of the other. But that is another big integral thing of e-stops. They have to be wired in series to ensure that everything after this switch becomes de-energized once it is activated. Now that we have the basics of this crap going on, let's wire some stuff up so you guys can actually see how it works and get a better understanding of what I'm talking about. Now, please bear in mind, this is a do as I say, not as I do kind of situation. This is for testing and training purposes here. This doesn't exactly scream safe, but I feel like in order to fully understand how something works, you need to see the guts. You need to know what's going on. So you guys can see here, I just have some Wagos on my field taps here that we can simply just put into this relay terminal here and energize this thing and get some function out of it. So first thing here, let's just get our common out of the way. This goes on one side of the relay. Or let me rephrase that. This goes on one side of the coil of the relay. That way, whenever we energize this thing, the energy has some kind of path to go back through. And everything will utilize this neutral here through my neutral bus. I'm going to take my normally closed field wire here, and I'm going to use that to energize the common of the relay, meaning the leg in there that switches back and forth. Remember that little lever that goes in between those two contacts? I'm going to put that one onto the normally closed, meaning that whenever my e-stop is pulled out, this leg is going to be hot. So that switch is going to be hot all the time, and whichever side that it goes to, that's which side the light will light. And lastly here, my normally open leg, I'm going to attach that to the coil of the relay, meaning that since this is normally open, that's attached to this green push button here. And whenever I push the button, it will energize the coil. So last thing we have to do here is smoke test. Let's release the e-stop. You guys can see here we have a red LED, meaning that my control circuit is on and the relay is in the normally closed position. Now, if I were to hit this normally open button, it changes the state of the relay, and so on and so forth. You can do this all day. Because we have power constantly on that switched leg of the relay, whichever position the switch is in, that's what output it energizes. Let's just take a little closer gander at how all this stuff works, shall we? So you can see here the circuit is energized, everything's on, everything works just the way it should. Take a look here at the inner workings of the relay. Whenever I press the button, this is the function that's physically happening. Let me try and shed some light on the situation here to make sure you guys can see it. So you see the contact here on the left-hand side, that is the normally closed. Whenever I press the button, it energizes that coil and pulls the switch to the other direction of the contact. Yes, this is incredibly simple, but sometimes it's the simple stuff that's the best. Now, in the event we have an emergency stop situation that we need to kill this entire thing, let's say the machine's going off the tracks or what, somebody gets in the way, whatever we need to do. No matter what's happening here, if the machine's running, it's functioning, it's doing whatever it needs to do, you hit the e-stop, it kills everything. You notice that our red normally closed leg is off because our control circuit is dead. And you can hit this button until the cows come home. Nothing's going to happen because of the way that the e-stop is wired in series, it de-energizes everything after it. So you can press this all day and nothing's going to happen until we clear the situation. We know everything is clear and we know it's safe. It's okay to re-energize the machine and the circuit. We release the e-stop and you see that my control power comes back on, indicated by the red LED here, and then we regain function of everything downstream of the e-stop, so it goes right back to the way it was. Now, just in case you're wondering, what if we have this thing in a circumstance where this button is held on? Let's just say a function is happening or something. Let's say that this is a latch circuit instead of a momentary switch. Okay, cool, let's simulate that. We'll hold this normally open in a closed position, and let's say something happens. Oh my goodness, e-stop. Check it out. It kills it regardless because of that series wiring. I cannot explain this to you guys any more intently of how important e-stop wiring is in series because of this particular circumstance. Whenever you have control power coming into a circuit, it needs to go through an e-stop first, some sort of limiting device, whether that is a PLC or an actual manual e-stop, something that kills the control power at the beginning of the circuit so nothing else down in the field can turn on if this is activated. Well guys, I know this is nothing earth-shattering and it's definitely nothing new, but I'm willing to bet that some of you have not been exposed to this stuff before. You know, like industrial wiring and specifically control wiring for like controlling and operating machinery and everything. And this isn't specifically just industrial stuff. I mean, look at your riding lawnmower. Have you ever got off the seat while you were riding it and the engine starts cutting out? Guess what? That is a wired in series switch that will kill the ignition coil. It's a safety, it acts as an e-stop. So in the event you fall off of your lawnmower while it's running, it kills the engine so you don't get run over and turn into hamburger whenever this thing rolls over you. You know, it's the exact same thing. It may be a different circumstance, a different scenario, but the fundamentals are there. If you guys understand how this stuff works, the difference between parallel and series wiring, you can really get a handle on how this stuff works and why we use it and why we rely on it so heavily. So I hope this clears some stuff up, and I hope maybe you guys even got a little something out of it. So if you like it and you dig it, drop a comment, let me know what you think, and we'll see you guys next time.